This is the mission 58, organized by Space Analog Station Habitat Mart. This mission is happening during November and December of 2020, and we have participants from India and Brazil. And today we'll have the presentation of Davi Souza from UFRN, the University Federal of Rio Grande do Norte. Davi, you are welcome to start your presentation, okay?
All right, thanks for the introduction, Professor Julio. I'm Davi Souza. I'm an electrical engineer student of UFRN, as Professor Julio mentioned, and I'm also a researcher at Habitat Marte. And today I will be presenting about the power station, the power center, of how would be the operation of this center in a Martian habitat. And I'm part of the crew 58, and it's a pleasure to be here. So these are the topics that I will be covering in this presentation. The design of the infrastructure. I will be explaining details about the technologies and machines to be operated in this facility, and I will be covering also other topics related to habitat management and also protocols and spin-offs. The initial consideration, I'm bringing here this picture, this pyramid of this paper, minimal number of cells for survival on another planet. I think this presents us a really detailed schematic of how would be an operation of an habitat on Mars, on another planet, no matter where we are, on the moon or Mars. And I'm considering here this pyramid that we have the energetic systems. The bottom of the pyramid are composed by the energetic systems and the industrial systems. So I will be explaining today with more details about the energetic systems. But as you can see, we have to consolidate, to integrate the energetic system and the industrial systems with the building and also with the ecosystems. So these are the main factors related to the power station and also to the engineering center in a Martian habitat. And in the top of this pyramid, we have the human factors, because we need to consider that no matter where we are dealing with humans. So there will be a lot of human aspects that will be faced in the Martian habitat, and we need to, and all of these systems need to have a good solutions for these, for some issues that maybe the humans will be facing. Related to the internal design, this is a proposal of Yash Hatod during mission 47, and here, as you can see, we have the power station integrated with the MOXIE, the solar farm, and also this is a proposal made by Eduardo, member of mission 56 and 56, and that he's proposing an eolic park integrated with the power station. And here I'm specifically integrating this eolic park with a solar farm. I will be explaining with more details about it, about this topic, why I'm doing that. And also the nuclear power, the 1 kilo crusty technology. And related to the logistic position of the infrastructure of the power station, as you can see, the nearest facility that we have is the engineering center. This is can be explained because the engineering center will be working into collaboration with the engineers of our station on the development of technologies and also maybe other solutions for the energy supply. This is the visual concept. As you can see, the power station facility. also a proposal by Yasha Todd. The internal design, I will be considering that all the facilities have a circumference shape with 8 meters of diameters and 3 floors. The idea is to provide a dormitory with beds for the astronauts, a small kitchen with a dining room, a toilet, an entertainment area, a food micro production model. We are considering here that we are in isolation process due to contamination in the habitat. So the structures, the facilities are isolated with the others. And so maybe we won't have the food available from the greenhouse. And related specifically to the power station, we have a monitoring area of the electronic systems of the whole habitat, battery storage area that I'll be calling the battery hub, with that will be not only the storage area with batteries, but I'm considering a bigger proposal for the battery hub and alternative generation units with other types of energy sources. This is the habitat design. I'm considering here for the ground floor a social entertainment area with the sleeping and toilet areas too. In the first floor, I'm considering the photobioreactors, the monitoring area, and also the protection systems. And the last floor, in this floor, I'm considering the battery hub. And this is, I will be, why I'm considering this, I will be explaining with more details during the presentation. I will be covering here most part of my presentation about the technologies, because I consider that the power station, we need to have an efficient energy delivery for the whole habitat, because their energetic systems are the main aspect when we consider the other systems like the life support systems, the environmental control. So to have life on Mars, we need to have energetic systems, and they need to be operating in an efficient and reliable way. As I mentioned, the technologies, the subsystems of electrical power are responsible for generating, storing, and distributing the power to the systems. As I mentioned here, the life support systems, the environmental control, also for some research related to the in-situ resource utilization and other technological systems. I can be mentioning here some surgical procedures on the health center. It's necessary to have a reliable energy supply, and also some backup systems too. Just an example. Some support technologies like automated systems to be operated autonomously. The idea of these systems is to have an optimal operational procedures and also quick procedures, because if we consider any emergency in these electric systems, this can be compromised. This could be compromised for the whole structure, for the whole habitat too. So also the data collection, detect failures, provide the balance of energy inside of the structure, specific structures, and also for the whole habitat, and also take some protective measurements. As I mentioned in the beginning of the presentation, we have the human factors in the top of the pyramid. So the protective measurements are really extremely necessary for these energetic systems. And I'm considering here some monitoring system for power statistics, the quality of energy. As I mentioned, in case of emergencies, the detection of faults, over voltage, over current, short circuits, atmospheric discharge, as we have during the dust storms, so just an example, and also energy fluctuations. This is also a possible case that the astronauts will be facing, like the energy fluctuation maybe we'll be compromising some systems and also maybe uh, turning off some systems, some vital systems. The equipments, I bring here some equipments, the batteries, the circuit breakers, fuses, transformers for measurements and also for protections. Here I can tell you the measurement transformer, the TM, and also the protective transformer, the TP. The converters and also inverters, and these we need to have our quick and reliable status of these equipments in case of any situation that will be happening. Some technologies necessary for the operation. I bring here a list of possible technologies. As I mentioned, the monitoring systems, some solar cells. I'm specifically bring during this presentation the OPV, that is the organic photovoltaics. Is a case of solar cells. It's a technology, a specific technology of solar cells. Solar filters, some thermal generators and radiators, batteries, capacitor banks, and I'll also bring here the FACTS, the FACTS devices. I will be explaining with more details too. Some wind turbines, electromagnetic floor. As you can see in this picture, we have some electro image. I'm not remember if this is the correct pronunciation, but we have this when we are walking through this floor, we can generate, as you can see, an amount of 5 watts. This is an alternative source of energy that are extremely necessary. That is extremely necessary for the astronauts in any case of the solar farm is not operating well, or any other system had failed. So we need to have these alternative generation unities. I bring here also the microalgae as a biofuel produced and cultivated in photobioreactors. Also some sources with mechanical energy like treadmills and bicycles, and other specific technologies that is the current division based on priorities, like depends on the system that we are dealing with, but with some systems that are with alternate current and other systems are with DC current. And so we need to have this division really organized, because we can also improve the efficiency of the systems. Like we have sensors that only operate with DC current, and other specific systems that only operate with alternate current. And also the mechanization for the monitoring environments. Some technologies, I bring here some solutions for the solar farm, the building integrated solar farms, the building integrated solar panels, as you can see in both right pictures. We have a solar panel that are into the building, that are covering the whole building. Also some malleable photovoltaic cells. I bring here also 2 pictures for you, and the OPV cells in a specific example of these malleable photovoltaics. I will be also explaining with more details. The heliothermic systems, and also solar ore, that is a technology like honeycomb photovoltaic. As you can see in the right bottom picture, we have small structures with small photovoltaic cells, and these we have a mirror that put the whole light into into this structure, and also all the lights that comes from the surface goes into one specific point. this increase a lot the energy efficiency of these technologies. Other solutions are in here, tracking systems, as you can see in the right picture, and also I mentioned the thermal energy, but we have also these solutions of called central power captation with solar radiation. So we can have the sunlight reflected for one specific point, one focus, but also we can have like a water pipe, water flow over this receptor, and that this water flow will be heated by the sunlight, by the radiation, and we can generate the thermal energy with the turbines. Also, I bring here a case of already happened on Mars. We have a lot of, as I mentioned in the beginning of the presentation, during the dust storms, maybe we'll be facing some situations that the astronauts will be facing some situations that they are not expecting. Like I bring here this example by NASA of this rover called Spirit rover. As you can see in the beginning, in the picture, in the top picture, we have the solar panel that are not covered with the sand of the Martian surface, and in the other picture we have the solar panels all covered. So this happened. I'm not remembering well when it happened. I will not remember, but as you can see here, we have the energy was cut from this rover and is not operating anymore. And I bring here also this graphic just to have an idea. This we have in yellow, we have the how much hours, and the tau measurements represent how clear or opaque the atmosphere is. So as you can see, in a specific period, we have a dust storm, maybe a dust storm that will generate this measurement, and this will be increased now energy produced. So I bring here two solutions. Solution in the left, as you can see the picture, we have the automatic photovoltaic cleaners. This already operates here on Earth in some deserts, an example in Negev Desert on Israel, and this works independently, and also has a water tank to wash the panels. But we also need to consider that the water availability on Mars is not as we have here on Earth. So this technology also works without water, emitting only a jet of air to remove the waste. Just a specific example to clean the solar farm. And also, as I mentioned in the beginning of the presentation, the integration of the solar farms with the eolic park. So in some cases that during the dust storms, when the solar panels are not functioning anymore, are not producing the necessary energy, we can have the use of the wind turbines, just to have an idea how the comparison of the size. I don't know if you can see well, we have here two examples of the Starship size, and we have the size of this wind turbine. So just to have an idea how the structure will be, we have a huge structure. So this will, when we are considering the payload of the rockets, this is a technologies that need to be operating, that will not be operating in the beginning of the habitat, but it's a solution, a great solution. As you can see here, we have on this reference, the wind speed during the dust storm, we have about 30 meters per second, and a turbine with 40 meters of size. of weight, we can produce an amount of 120 to 300 kilowatts. So this is a good solution, a good source of energy too. And the most, I can tell you the famous one that NASA is working on it too, I think will be the most achievable and the technology that will be producing energy in the beginning of the settlement on Mars, on the Mars surface. We have the kilopower reactor using Stirling technology, the crusty. Is a technology designed to be safe, long-lasting, reliable, scalable, energy efficient, and also, as I mentioned, related to the payload, compact to fit inside the rock. So this structure, we can have a lot of these structures inside of one rocket. And in 2017, 2017, NASA tests generate about 100 watts of electricity with this technology. And we have the idea of this technology is to be scaled. So it can be scaled to 10 kilowatts or even achieve megawatts of generation. So as I mentioned, the battery hub, I'm considering in the top, the second floor of the structure, this battery hub. So what I mean, we have the power storage with a lot of batteries. As you can see in the left picture, we have the batteries that are associated in series. So we have an amount of energy, of power that can be storage. And these batteries need to have heaters and radiators to to circulate the air inside of the hub, because there are some examples of batteries in previous rovers on Mars due to the low temperatures that they face. These batteries doesn't work anymore because the batteries, we have the electrical chemical process. So if the temperature is not dealing with some issues like this, so it's necessary the heaters and the radiators. And also I'm considering here capacitor bank to provide the reactive power of the systems. And I bring here this solution, this interesting solution that I was searching this week, that is called the flexible AC transmission systems. And as you can see in this diagram, we have a devices. It's not only one, but we have solutions of devices that in case of when the power demand increases, we will have an unstable operation hours. So we have an optimism tool that will be avoiding the oscillations of the power generation. So this would be necessary to have an optimal solution in the voltage stability, and also this will decrease the costs associated to this instability of the systems. Also, a battery recycling area I'm considering here, like we have a lot of chemicals inside of these batteries, so I think won't be useful, won't be safe for the astronauts to have the disposal of the batteries on the surface of Mars or other places in the structure. So I'm considering here in the second floor of the structure an area to have the recycled materials storage, or even if necessary, if possible, doing any kind of reuse process. Also, in the inverters and converters, as you can see in the left picture too. I bring other technology, as I mentioned, the monitoring systems. The idea is to monitor the parameters of the energetic system of the grid. The idea is to have artificial intelligence to generate some reports, and also accelerate the maintenance and team productivity, and also made also have some short repairs in short times, and also prioritizing some tasks. Like we can, with these monitoring systems, it will be possible to identify where is the specific point that we have like a fault or a problem in the system, so we can identify where it's happening and will be more fast to conduct any kind of maintenance in the system. This is an example panel. It's really simple. Just to have an idea, this is available in a commercial website that we have here in Brazil called Mercado Livre. So it's really simple, and we can find many other solutions like this. Possible resource to generate in situ or be transported from Earth. I always like to talk about the algae cultivation, because it's an alternative source of energy, and not only energy, as I mentioned, but it can be an edible biomass, also provide a CO2, carbon dioxide to oxygen conversion, and also effluent treatment. So we have into one technology, into one solution, into one technology, many solutions. And I also find this interesting approach for the algae, fuel cells, biophotovoltaic. It's a solar cell with made by algae. It's really interesting. And as you can see, it has a power density of 0.5 watts per square meters. So if we can scale this, we can generate a lot of energy. And in the right picture, we have just some approach made by NASA related to the green technologies, such algae. Other resource that we can generate in situ, we have structure. It's a structure. The MOXIE is called Mars Oxygen In Situ Resource Utilization Experiment. And the idea is to produce oxygen, fuels, feeder circuits, and also the idea of this structure is to have a network optimization to reduce the consumption costs. So it was sent in the Perseverance rover. We have a prototype, a small prototype, to see how efficient this technology will be, and why it's considered this technology associated and integrated with the power station, because we have, as you can see, we have a lot of electric, mechanic, and chemical structure devices. So it will be necessary if we have, this is a small prototype, but if we scale it to generate for the whole habitat, we'll have it will demand more energy supply. So that's why it will be better to have this structure integrated with the power station. Also, the idea, as you can see, the MOXIE is to the characterization of the size and morphology of the atmospheric dust, to verify the effects of the operation of surface systems. And if we consider that on the Martian atmosphere has an amount of 96% of CO2, it will be the better approach to transform and to provide the oxygen for the astronauts for the whole habitat. This picture, as you can see, is just the process of electrolysis made by the MOXIE. The management of the habitat, I bring here to the organizational structure the proposal for the grid, for the network. In the top part, as you can see, we have the power station associated with the photobioreactors, the monitoring area, and the protection systems. This would be the first floor, the source of the energy demand on the first floor. And in the ground floor, we have the social area, the food microproduction, and the sleeping area. So now I'm considering, as I mentioned in the beginning of the presentation, the last floor, the second floor, is the battery hub. why I'm doing that, why I'm putting this structure in the top of the structure, and the idea is to be decoupled. We can have an structure to isolate efficiently the battery hub in any case of fire, of anything, any emergency situation that will be happening in this battery hub or even with the systems. Just to have an idea, the protection systems will be first of the battery hub. So the energy supply that will be coming from the solar farm and the nuclear power will be passing through the protection systems, and then we go to the battery hub. So we need to have the protection systems actuating before we have any kind of emergency. So if this emergency arrive on the battery hub, it can compromise the whole structure. So that's why I'm proposing here this decoupled structure, isolated structure in the last floor. And in this area, we will have, as I mentioned, the recycling area. So if we have some fire, maybe the chemical of the batteries won't be good, won't be safe for the astronauts, and the power control. So we have a lot of heating that will be also really unsafe for the astronauts. Related to the organizational structure too, as I mentioned, we have connected infrastructures, especially, not also, but especially connected with the engineering center. And why I'm doing that? Because we need to have the redundancy systems. We won't have the protection systems only on the power station. We need to have all the protection systems in the engineering center, because if the systems of the power station, if the protection systems of the power station doesn't work, we can't compromise the whole infrastructure, the whole settlement. That's why I'm bringing here other protection systems to make the redundancy of this protection. The idea is to have the professionals capable to conduct experiments aimed at grid structure and systems maintenance, and also conduct some specific research related to the energy systems in collaboration with the engineering center. So I will be mentioning the 3D printing, some technologies, some solutions with 3D printing. The idea is to have this collaboration between the engineering center and also the power station. And waste management, the idea is specifically the material waste management. So it's necessary to analyze what material can be discarded and what materials can be reused, and also providing equipment recovery, reuse logistics, and also disposal logistics. The positions, I bring here two permanent positions, the power manager and the chief engineer. Power manager will be responsible to conduct good practice and awareness into the whole habitat and develop the monitoring and maintenance schedules. And the chief engineer will be a professional strictly qualified to conduct in situ activities, like in any case of necessary maintenance in the solar farm or the nuclear power. This will be responsible to install, not only install these equipments, but also conduct their maintenance routines. So, some functions that can be engaged in this structure. We have the head, the sub-chief, the analyst, and the maintenance. And I also propose here to not have one astronaut doing the same activities during a long period of time. When we are considering the psychological aspect, the well-being of the astronauts. So it's necessary to provide other stimulus for them. So that's why I'm proposing here to have like an alternance of these functions between both astronauts. The duties of the chiefs is to delegate these functions, give structures, establish the schedules, and promote the rotation between the respective center, the power station, and with the other infrastructures of the habitat. Related to the astronaut training program, I bring here some basic features that I consider incorporated. We need for the whole habitat to provide a sustainable human presence in space. Also support the long-term effects of isolation. As I mentioned, the human factors are extremely necessary to be considered in the whole systems. We also, it's necessary to provide some practice to reduce costs and technical risks in overall systems. Also provide some courses focused on basic understanding and of the handling and maintenance of electrical systems. If we are considering an isolation between the infrastructures, like if an electrical system in the greenhouse, for example, or in the health center is not working anymore, it's necessary for the astronauts that are there have a basic idea what is happening, and also to provide the reports for the like a remote report for the power station, and also in any case of like to conduct any kind of activity of maintenance, the responsible in the power station can conduct some remote video, as we are having here, to provide a lesson, a small idea what can be done, and also to supervise what the astronauts are doing during these activities. Also conduct analysis of risk and failures, allowing the generation of monitoring reports of the systems. That's why it's necessary this basic understanding. Meetings for crew decision making, and also provide have the astronaut program inside of the habitat, provide some simulations and some trainings to overcome emergency based on situations identified at Mars. So we have an idea of what can happen on Mars, but maybe the astronauts will be facing new situations that we can even imagine for now. Some videos that I bring for you here. The solar or energy, the honeycomb, photovoltaics, video about the kilopower nuclear system, also about the MOXIE and the Ecopia E4 robot. It's the one robot that conduct the cleaning of photovoltaics in one desert. The resource necessary for 1 week, considering the basic needs of the astronauts, I bring here the number, the 2 astronauts in the structure, the food, the diet of the astronauts will be determined by the biotype, the protein will be specifically for each astronaut. And I'm considering here a daily consumption of 2.1 kilograms by person. And if we make the calculus during a week for both astronauts, we will have an amount of 40 kilograms of food. And considering the potable water, the drinkable water, I'm considering here, as we have here on Earth, the 3 liters of water by person. So as I mentioned, this can be different in the case of Mars. Like, for example, about health, what we know about health, it's based on the situations we face here on Earth, but health on Mars can be different. Just an example to have an idea. The same thing for the systems, the same thing for the situations, and the same thing for the water too. So I'm considering these 3 liters. Our week consumption will be 42 liters of water for both astronauts, and I'm not considering for the systems and also for showering and washing dishes and these things too. And related to the energetic needs, the resource, the dimensions of the energy supply, water supply, heating and air conditioning systems, will be determined by the number of inhabitants and the amount of vegetation inside of the environment. So this will be based, the energy supply will be based on these, both the life systems, the life inside of the structures, the inhabitants and also the vegetation. And according to James Reuter, the Associate Administrator of NASA Space Technology Mission Directorate, he tells that it will be necessary about an amount of 40 kilowatts of power on the surface of Mars. So if we are considering that the nuclear power technology works well and produces that amount of energy in a reliable way, so we can achieve this amount of power easily. Also need to consider the emergency situations, like if this system fails, that's why we need to have other source of energy too. I believe that all the sources are welcome, and as much sources we have will be better and reliable and resident for the whole habitat. The guidelines to be provided to the other facilities. I'm proposing here the indicators of consumption and control of energy use, the economy practices to be added to the astronauts' routines, basic guidelines, training for handling and preventive maintenance of the electronic equipment, smart reports capable of establishing the correlation between the different variables and maximizing the energy efficiency. So it's necessary, the artificial intelligence will be extremely associated with this. Also, the protocols for energetic guidelines that I will be presenting with more details, and the warnings about failures and emergencies that is really necessary. Like if happen emergency situation in the main station and the astronauts in the main station doesn't see, like it's necessary that the power chief or the people inside of the power station see this emergency happening, and also provide the guidelines for the main station. Related to the protocols, I bring here the protocols related to this routing. I'm proposing here the track system notifications related to deviations and irregularities. So it's necessary to track the specific point, or if we have any kind of irregularities in the system, and also remote monitoring for the life support systems and also environmental control. And I bring here the controller with some sensors. We will be having sensors in these the 6 boxes, just to have an idea. The grid, the generators, the batteries. So we have the sensors, specific sensors to collect the necessary parameters in these 3 topics, in these 3 areas. And also we will have sensors for infrastructures, the high loads of the whole habitat, and also the protection devices. And the controller will be providing an interface, a machine operator interface with the system status for the whole inhabitants, the whole astronauts. Protocol for safety. As I mentioned, the emergency decoupling procedure, that area, the isolation area in the 2nd floor of the power station, in case of failures, faults, short circuits, lightning strikes common in sandstorms. So it's necessary, if necessary, start the emergency decoupling of procedures, and to see if it's necessary, like to isolate the whole structure or isolate in a specific system. Also the protection, the idea is that the protection equipments and sectioning of generation plants and habitat will be activated to avoid the widespread losses. And people inside of the structure must start the process of checking the status of the protective equipments. That's why it's necessary the sensor in these equipments too. And if necessary, establish an order to deactivate the system, the specific system and activate the bank of generators, of alternative generators and backup batteries. Also, some other protocols, the system recover, in any case of if necessary, any maintenance in the solar farm outside the habitat, outside of the structure, it will be necessary to conduct an AVA, an extravehicular activity to monitor and assess the affected site and perform the inventory of losses and recovery schedule. And related to guidance for the host, for the other structures, inform to the other mission members about the maintenance or repair. Related to the protocols for occupancy and entertainment, I propose here some activities like mainly the alternation of monitoring routines. As I mentioned, it's necessary to provide different stimulus for the astronauts related, associated to the mental well-being of them. Socialization practice proposed by the health center, relaxation areas, also conduct, have some physical exercise, games like board games and video games for the astronauts, and other operational activities involving the cultivation of food and interaction with the plants. So if we consider, if we have the microfood production module, this will be possible, will make easier this interaction with plants for the whole astronauts, for all the astronauts. And the protocols for food microproduction. I bring here this picture that was a result of a paper called Agriculture in Mars, Habitat Marte Finest. This is a paper made by me and Professor Julio. We presented this paper during the IAC, the Cyber Edition in this year, and we have during the year of operation of the Habitat Marte greenhouse, the biohabitat, was possible to the routines related to management, maintenance, recycling practice, and harvesting and processing. And some activities that we developing in these routines are analysis, diagnosis, ensure the circularity of the systems, assure the fidelity of the methodologies of the protocols that we are applying, the orientations, and also detect possible failures of the systems. And the idea of these protocols are to ensure the following features. As you can see, the food logistics, the risk management and prevention and monitoring reports to be provided for the greenhouse, and waste management to, like if we have any wastes, if each structure have a small biodisaster, this weight, or also, I'm not remember the word now, but a compostier. So if each structure have a compostier, it will be a good solution for the food waste management. And related to the 3D printing, as I mentioned, it's necessary to have the cooperative work between the energy center, or the energy center and the engineering center for the production of eco devices. As you can see in the right picture, we have a device made with organic materials, also organic electronic devices. As I mentioned, there's the photovoltaics, the OPV, the OPV cells, also equipments, coverage and shutters. Also, you can see this right picture too. Conductors and filaments. You can see in the left picture we have like a small circuit made with filaments of 3D that was developed with 3D printing. So we have the battery associated that we can turn on these LEDs, so it can be also scaled and would be a good solution too. And also for 3D printing, as I mentioned, the organic photovoltaics, some features associated to it is related to the low-cost manufacturing. Just to have an idea, it reduces the cost by 50%. A lot of abundant materials. Also, I saw some other reference that tells that it can be useful. Also, recycled materials. The flexibility, as you can see in the picture, the low weight. Also, you can see in the picture is really thin cell, a proper disposal, and also one amazing solution that these technologies can be 3D printed. So just to have an idea, these 3D printed solar panels are 20% more efficient than traditional panels. So we have a lot of solutions associated to it. The spin-offs, some technologies that could be applied on Earth, like we will have structures with efficient resource saving, like as you can see, just an example, this picture shows you a roof with solar cells, and we can like it have a good design, and also provide the lighting, the external lighting coming from the sun to goes into the building. So it will be it will be useful to save energy that is with lighting, with the lights, with LEDs. Also, a self-sustainable electricity production. We have, as I presented, the technologies. We have a lot of solutions that provide this production, this sustainable production of energy. The delivers with lowest possible handling and better performance for the smart grids. So this, just to have an idea, just to present you, these conductors, these filaments, is one possible solution to be used in the smart grids. Like if we have the sensors that are outside, that are in the external environment. So I think this would be really useful to provide a better performance, to avoid oxidation of filaments. Like if we have a filament made by iron or something like that. So this would be a good solution if we have a 3D printed, because it will have lower costs and also will keep the reliability of the system. And also environmentally friendly technologies with carbon footprint reduction. And just to have an idea, each square meter of the OPV, the organic photovoltaics, avoids the emission of 120 kilograms of CO2 of carbon dioxide per year. So it's really necessary and extremely necessary when we are considering the climate crisis that we are facing during these years. The guidelines to be applied to daily life on Earth it will be providing the creative ways to deal with solar energy ISOs, as I presented the systems to cleaning the solar panels, the development of new technologies and systems to keep the reliability of the energetic systems, as I mentioned, the filaments and many others, the FACT devices too, easy assembly and maintenance with optimal procedures, solutions to keep the confidence related to control of power and its protection systems, the monitoring systems and automated systems associated with the power generation and power transmission lines, reuse of materials and recycling practices. An example of the solar organic photovoltaics, it's if we are considering that the traditional photovoltaic the solar cells have a lifetime of 15 years or 20 years. So after this period, it needs to be disposal, and it will have we have a lot of materials that can't be recycled. So if we have our organic technology using in these systems, would be better for the disposal and reuse of the materials. Also energy consumption management, the driving currents and efficiency in electric transmission lines. So in the energetic field, in the energetic sector, we are passing throughout like a revolution. The idea is to have in the future, we won't have any more the devices, the equipments that operate with alternate current, because this causes a lot of oscillations in the systems and also burns a lot of equipments. And the idea is to have in the future more and more DC current devices. And also provide investment in research on different ways of adding positively the global energy metrics and the impacts on sustainable development goals. We have the SDG 7 related to the clean energy, SDG 8, the decent work and economic growth, the SDG 9 and 12 related to consumption and innovation related to infrastructures. And as I mentioned, related to the carbon footprint, the climate crisis that we are facing, it's necessary to have this idea. I'm bringing here during all of my presentations, and I believe that this is really necessary to be explained, to be presented here. We as researchers and maybe future astronauts, I hope to, we need to have this idea that space technologies are useful not only for Mars, for space, for the moon. These are not only solutions that are useful for space, but we need to have the idea, the concept that it can be useful also for Earth, here on Earth, and also can provide us a lot of solutions to overcome the climate crisis and to make our world better and more, and start the regenerative process of our planet. So these are my references. Thank you very much. Thank you for your attention, crew. And for those who this is my email, and I'm open now for questions and comments from my crewmates. Thank you very much.